Hello students, good morning all of you. So today we will begin with our module 10 of our video lecture, and as you all of you know, for the last two modules we were essentially discussing about the different bodies, okay, and their moment of inertia. We calculated or derived expression for computing the moment of inertia of different regularly shaped bodies, okay, sphere, cylinder, rings, and so many other objects, regularly shaped objects, and their moment of inertia we calculate in simple formats. And in today's module, we will familiarize ourselves with some theorems on moment of inertia. Okay, some theorem exclusively using moment of inertia of different bodies. How to calculate moment of inertia of different bodies using certain theorems. Okay, that is the current topic in today's module. We will discuss that. First one will be about parallel axis theorem of moment of inertia. So after studying this theorem, what is the use? The use is that you can apply this theorem to find the moment of inertia of different bodies with respect to different axes. Okay, with respect to different axes, we can find the moment of inertia. That is one of the application of this particular theorem. So let us see how this is done. First of all, consider a sheet. Okay, a sheet or an object or anything like that, and you have two axes. You can see in the figure. One axis is actually passing through the center of mass point of the body, and there is another axis parallel to this, which is passing through some arbitrary point. But keep in mind, the first axis is passing through the center of mass point, and you can call the moment of inertia with respect to the center of mass as I0. Okay, I0, and you can count the moment of inertia of the body with respect to the z-axis as Iz. Okay, Iz is some other axis. The moment of inertia with respect to this z-axis is called Iz. Okay. That means you can rotate the body with respect to center of mass axis. You can rotate the body with respect to the z-axis. So in both rotation, there will be some moment of inertia. Actually, this theorem relates moment of inertia of the body with respect to the center of mass axis and moment of inertia of the body with respect to the z-axis, which is an arbitrary axis at some distance from the center of mass axis, and they are parallel. So that is the sense of parallel axis theorem. So the condition is that both these axes should be parallel to each other. Okay. So let us see the theorem now. Okay. In fact, this theorem enables us, help us to calculate the moment of inertia of a body about any axis. Okay, that is very important. Any axis, provided we know the moment of inertia of the body with respect to the center of mass axis. Okay, with respect to center of mass axis, we call as ICM, or as often we call I0 also. Many terms are used, and with respect to z-axis as IZ. Okay, so then its relation is like this. Okay, moment of inertia with respect to the z-axis is equal to moment of inertia with respect to the center of mass axis plus mass of the whole body. M is the mass of the whole body, and what is d here? You can say d square here. D square is the perpendicular distance between the axes. Perpendicular distance between the axes, that is d. Okay, so Iz equal ICM plus md square. This equation is actually parallel axis here. Now let us define it in a way like this. The moment of inertia I of a body with respect to an arbitrary axis, that is this one, is equal to the moment of inertia of the body about a parallel axis passing through the center of mass, that is I0, plus the product of whole mass of the body and square of the distance between the two parallel axes. That is what we earlier said. Okay, Iz equals to ICM plus MD square. In many books you can see instead of ICM you can also write I0. So in order to designate it specifically we use ICM. So it is quite easy to memorize. Okay, so I hope the idea is clear. Now we have stated the theorem, but we have not proved it. So now let us try to prove it. Okay, how this is proved by the parallel axis theorem. Okay, using this you can find moment of inertia of many objects with respect to many axes, provided that they are parallel to the ICM axis. Parallel to the ICM axis. So let us see the proof. Okay, we have a irregularly shaped body here. There is two axes. One axis is Z axis, which is passing through the center of mass point of the body, and there is another axis which is parallel to the Z axis at a distance d from the center of mass axis. Okay, so that is exactly given in the figure, and you are considering a particle. Okay, you are considering a particle at a distance say ri from the center of mass axis. Okay, so there are so many other particles, so you can have a moment of inertia with respect to Z axis, no problem. And so that is what is given here. So consider any body at okay with a particle mi at a distance say vertical horizontal distance xi. Okay, so there are infinite number of particles, and the moment of inertia of the whole body. Okay, moment of inertia of the whole body with respect to this axis. Okay, z axis will be equal to mi xi square. Mi xi square. So okay, so here this is the axis. Okay, what I here indicate the moment of inertia of the whole body with respect to the I axis. Okay, that is very clear. So summation indicate that whole particle, each and every particle is moving. So this is the I which we get if you revolve the body with respect to the Z axis. Okay. So and that is there. And from the figure you can see that in fact the x is equal to ri plus d. This is x and that is equal to ri plus d. What is ri? Horizontal distance from the center of mass axis, and d is the distance between the two axes. Okay, that is clear from the figure. So we can remove the xi here and substitute ri plus d as shown in the figure. So what happens? You will get I is equal to mi into xi is ri plus d. So ri plus d all square. We have written it. Now we can square it. Ri plus d all square. You can take the square. So what happens? I is equal to summation mi. This is something like a square plus d square plus 2ab. Okay, so you have ri square first, then mi d square second, then there will be a 2ab term that is given here. So you have 2 mi ri d. So this way there is three terms are there in the result. Now let us investigate term by term. Each and every term we can investigate separately. Let's see what are they. Okay. So the same expression. First let us take the mi d square term. Mi d square is one. Okay, that is what is shown. So in which d square can be taken outside and you have summation of mi. Summation of mi is nothing but adding the mass of each and every particle. When you add the mass of each and every particle, you get the total mass of the body. So that is given as capital M. So mi di square now turns to be d square into m, capital M. Okay. So take the next term, that is mi rid. So 2 is a constant, so nothing will happen. And d you can take outside since it is a constant. and inside you will have summation mi ri. So in fact, this is the summation with respect to the center of mass point, and summation with respect to center of mass point will be equal to 0. Everywhere m1 r1 plus m2 r2 is equal to 0 when we take that with respect to center of mass point. So mi ri is equal to 0. So what happens? The third term now becomes 0. Okay, with obvious reason, third term becomes 0. Now again rewrite the equation. What we get? I equals summation mi ri square is already there plus md square. Okay, md square, and summation mi ri square is nothing but moment of inertia of the body with respect to the center of mass axis, mi ri square. It is obvious from the figure, and md square is written in the same way. Nothing. So hence we prove it. Moment of inertia of the body with respect to any arbitrary axis is equal to moment of inertia of the body with respect to the center of mass axis plus mass of the body, the total mass of the body, into square of the perpendicular distance between the axis. So this is the proof. Okay, so we stated the theorem, explained the theorem, and subsequently we could prove that this is exactly true. Okay, hope the idea is clear, hope the derivation is clear. Now let us move to the second theorem, that is called perpendicular axis theorem. Before explaining the perpendicular axis theorem, I would like to say that this is applicable for lamina or sheets. Okay, you consider a two-dimensional sheet lying in the xy plane, lying in the screen plane, and there are three axes: x-axis, y-axis, and z-axis. X and y lies in the plane of the sheet, and y is perpendicular to it. Okay, no doubt. So then the theorem it goes like this: moment of inertia of a two-dimensional object about an axis passing perpendicularly through its plane is equal to the sum of the moment of inertia of the object about any two mutually perpendicular axes lying in the plane of the object. So what does it say? In fact, it says that if you consider the moment of inertia of the lamina with respect to z axis as iz, then that particular iz will be equal to sum of the moment of inertia with respect to the x-axis and moment of inertia with respect to the y-axis. Okay. Ix plus Iy will be equal to Iz. So this is what it says, and as you know, the theorem can be used to find out the moment of inertia of an object with respect to different axes. If you know about x-axis, you can even find about y-axis, you can even find about z-axis. So there are so many applications by making use of the perpendicular axis theorem. So we stated here, but not proved it. So now let us try to prove the perpendicular axis theorem. So again, consider the same sheet, same two-dimensional lamina. Axes are given here, x, y, and z axis. And what we are going to do is, so you consider some point on the sheet. Let P be a point where some mass is lying, and mi be the mass of that particle at the point P, and let r be the perpendicular distance. Okay, perpendicular distance of the particle in the z-axis. And obviously we know there will be a moment of inertia for the lamina with respect to z-axis. What about the moment of inertia of the particle, this particular particle with respect to z-axis? Obviously that will be mi ri square, no doubt. A moment of inertia of the single particle about that z-axis will be equal to mi ri square. And if you want to calculate the total moment of inertia of the disk, you have to just sum up it. So summation of mi ri square. Summation of mi ri square give you the moment of inertia of the entire lamina with respect to z axis. That is given here as I z is equal to summation mi ri square. And from the figure you can see that ri is a hypotenuse of this triangle OMP. If you consider OMP as a triangle, then ri is nothing but the hypotenuse. So from the figure you can write that xi square plus yi square will be equal to ri square, isn't it? Xi square plus yi square is equal to ri square. So why not? You can replace your ri with xi square plus yi square, no doubt. So when you do that, you can see you can separate these things. You can separate the first one summation mi xi square, again another summation mi yi square. What is this actually? Summation mi xi square. It is nothing but the summation of moment of inertia of each and every particle with respect to the x-axis, isn't it? The first term simply represent moment of inertia of the entire lamina with respect to x-axis. That means if the lamina is revolving about the x-axis, this will be the moment of inertia. And second term indicates moment of inertia of the entire lamina with respect to y-axis. That means if you rotate with respect to y-axis, this will be the moment of inertia. So you can replace mi xi square with ix and mi yi square with iy. So we obviously get iz is equal to ix plus iy. So this is what is the theorem. Okay, we already said that moment of inertia about the z-axis is equal to sum of the moment of inertia about two mutually perpendicular axes lying on the plane of the lamina. This is obviously given here. So hence the proof. So we could prove first the parallel axis theorem and secondly the perpendicular axis theorem. So we stated and proved. Now obviously you can do many problems related to this theorem that will be definitely accommodated in the classroom. Okay, so now let us move over to another topic that is also coming under angular momentum chapter. That is about Atwood machine. Also, it is a mechanical device used by what is called the English mathematician George Atwood to demonstrate many experiments, many theories on mechanical bodies. Okay, many theories on mechanical bodies. He demonstrated, he proved it using this particular mechanical apparatus, which is it is nothing but a pulley is there, two masses there, and these two masses are connected with a inextensible string. Inextensible means its length cannot be changed. Length is a constant. Whatever mass you attach at the both end of the string, its length is never going to be changed. So such a string is called an inextensible string. And depending on the masses, weight, etc., the string mass system can go in either words, okay, either in the positive direction, either in the clockwise direction, or in the anti-clockwise direction. That depends on the mass. Okay. So using this particular apparatus, you could prove many theorems. Okay, that is what we are going to study today. It is known as Atwood machine. In fact, an ideal Atwood machine consists of two objects of masses m1 and m2 connected by an inextensible massless string over an ideal massless pulley. Okay, I hope the idea is clear. And in this topic, what we are going to do is actually we will connect the two masses at the edges, okay, end of this string. Masses will be of dissimilar value. So what happens, depending on the mass values, there will be an effective force or tension on the string. Accordingly, the string will move. And using that, you can find out the acceleration of the masses. Okay, acceleration of the masses. So that is what we are going to do. So what in fact happening is, when there is a mass difference, what happens? There is a net torque acting on it. There is a net force acting on it. And the force is acting at diametrically opposite sides. Such forces will constitute as a torque. As you know, forces acting at a distance will constitute as a torque. So due to torque, what happens? The pulley may revolve. Pulley may revolve with some angular velocity, sometimes with some angular acceleration also. If angular velocity changes, there will be an angular acceleration. So with that acceleration, the pulley will revolve. Well, then we can find out many physical parameters. That is our purpose. Okay. So consider this output machine, and there are two masses M1 and M2 attached at both ends, and assume that the pulley is of some definite mass. Pulley is of some definite mass, capital M, and assume that the radius of the pulley, it is something like a cylindrical object. Okay. So consider its radius is R. Okay. Radius is R. So when it is purely rotating, okay, we can consider the masses are experiencing some force. Suppose M1 is moving and M1 is moving with some acceleration. So net force, that is M1A, can be written as M1G minus T1. You may surprise what it is. I will explain you. M1 into A is the acceleration of the body downwards. Okay. Net acceleration. M1A is the net acceleration. What is M1G? It is the actual force acting on the body downwards due to the earth. So what is T1? T1 is nothing but the tension acting in the upward direction. T1 is the tension acting on the body in the upward direction. So T1 is upward and M1 is downward. Understand? M1 is downward. So what happened? This is the M1G minus T1 is the net force acting on. So net force is actually mass into acceleration. So we get M1 into A. So M1 into A is equal to okay, is nothing but the effective resultant force acting on the body M1. Okay, M1G minus T1 is the net effective force, and force is equal to mass into acceleration. So we get M1A is equal to M1G minus T1. Okay, this is the equation at the mass M1. Similarly, you can have an equation at the mass M2. There is an mg acting downward, isn't it? And there is of course a T2 acting. So what happens? T2 is acting upward, of course, and M2G is acting downward. So we have written here. Since the mass body is moving upward, here let us assume that the force is M2A. Okay, one of the force should be upward and the rest of the other one should be downward. Only then there can be a motion. So what happened? M1A, M2A is equal to tension minus M2G. M2G is acting downward. Okay, so we got the equation of motion at the two bodies. So in order to find the net force, what we can do? We can simply solve both the equations. In fact, we can solve it. So before going that, assume that there are two tension. One is downward, one is upward, and due to the resultant force, the pulley experiences a torque. Okay, pulley experiences a torque. You can assume that is torque is tau. So due to the torque, what happens? Pulley revolves with an angular acceleration alpha. Okay, you have studied that alpha is called angular acceleration, and angular acceleration and torque is raised as torque is equal to I into alpha. Hope this is clear. So torque is equal to I into alpha, and torque is nothing but force into distance. Okay, torque is equal to force into perpendicular distance. So from the figure you can see that the net force is T1 minus T2. T1 is due to the mass 1 and T2 is due to the mass 2. And the resultant tension is acting on the pulley actually. So the tension is nothing but force. Okay, so this is the resultant force acting on the pulley. So force into perpendicular distance. Okay, that is the torque that is equal to I into alpha. Okay, hope this is clear. That is acting with respect to the point, the center point. That is why R is taken. We have not taken 2R. Why? Because the force is acting with respect to the axle of the pulley. Okay, otherwise we could take a 2R, but we have not taken a 2R, we have taken R because our center point is this one. Okay, so torque we replace with the T1 minus T2R. That is equal to I into alpha. Okay, this one we already studied. And already you have written that M1A is equal to M1G minus T1 and M2A is equal to T2 minus M2G. Okay, so if you solve it, what we get? If you subtract the first one from second one, okay, we can do that. So we just add both the equations. So we have M1G minus T1 plus T2 minus M2G is equal to M1 plus M2. Just added both the equations. So on adding, what happens? We get T2 minus T1. Okay, just modify the equation. What happens? M1 minus M2G minus T1 minus T2 is equal to M1 plus M2. Once again modify the equation. For that what we need, T1 minus T2 is already given as I alpha by R. So we replaced our T1 minus T2 with I alpha by R. Okay. Again proceed. Let us modify little bit. We modified it like this. Okay, M1 minus M2G minus I alpha by alpha. Okay, again alpha here. Alpha is nothing but an acceleration by radius. You know, V is equal to R omega. You are studied in your school classes. And A is equal to R into angular acceleration. So alpha can be replaced with acceleration by R. So we replace alpha with A by R. So what happens? The second term become now IA by R square is equal to M1 plus M2A. Okay. So we want to get the expression for acceleration. Okay, that is our purpose. What is the net acceleration of the system? Okay, with what acceleration? The body will revolve down. Okay, when you leave the system, with what acceleration? The body will come down. That is what we are finding. So we modified once again. We took M1 minus M2G here and brought the other term to the right hand side. So we have now M1 plus M2A and minus IA by R square. And RA can be taken out, obviously. So now you see your acceleration A will be equal to left hand side divided by this term, bracket term. So we get A is equal to M1 plus M1 minus M2 divided by M1 plus M2 plus I by R square into G. Okay, G is coming here. Please note on it. So we got the expression for acceleration of the body. Okay, with respect to what acceleration? The particle or the body will fall down. You can experience the same thing. Suppose when you are taking up water from a well, and suppose by mistake it slipped. Suppose the bucket got slipped from your hand. You can note the same phenomena in a well. Okay, domestic activity, you must have encountered such situations where you can see the bucket goes down to the well with a tremendously high acceleration. Okay, this is one of the instant, day-to-day instant you can note down, where you will note on this phenomenon. Okay, so M1 minus M2 by M1 plus M2 plus I by R square into G. So this is the acceleration. Okay, and here you can replace your I. Why? Because I is the moment of inertia of a disc. Okay, you can compare your pulley with a disc or a cylinder, and moment of inertia of a cylinder is given by I is equal to mr square by 2. Obviously, we have studied it in one of the previous module. So replace your moment of inertia here with mr square by 2. You can replace it. Yeah, I is replaced with mr square by 2. So what happens when you substitute mr square by 2 here? R square will be cancelled. You will get it. Acceleration is equal to m1 minus m2 by m1 plus m2 plus m by 2. Okay, obviously. So our expression now got modified, simplified, and now we have only masses here. And this is acceleration. So if you want to find out the velocity of the body, acceleration is equal to dv by dt. So you can replace your a with dv by dt. So we get a dv by dt is equal to m1 minus m2 by m1 plus m2 plus m by 2 in g. Okay, so in order to find the velocity, you just integrate it. Velocity will be equal to integral m1 minus m2 divided by m1 plus m2 plus m by 2 into g into dt. Okay, so integration is applicable only for time. If you take initial time as 0 and the final time at t, you will simply get the velocity is equal to some constant into time. That is m1 minus m2 by m1 plus m2 plus m by 2 gt. Okay, you can write gt. So we'll substitute the value of time, say 10 second, 20 second, whatever time, you will get the final velocity. Okay, very beautiful equation here. Here integration is not a complicated thing. Very simple, just integrate dt, that will be equal to time. Understand? So we got the expression for velocity. And even if you want, you can again cut down the relation, cut down the equation. Suppose the mass of the pulley is very small, then m can be neglected. You can neglect it. Okay, so this will be 0. So what happens? Velocity equation again simplified. Okay, we get velocity is equal to m1 minus m2 divided by m1 plus m2 g. Okay, velocity, acceleration due to gravity is still there. So simple. Even integration you can remove. You can simply write without complication m1 minus m2 divided by m1 plus m2 into gt. Okay, that's also possible in simple cases. So you can do lot of problem based on this particular equation. Okay. So here is a simple question. You can do it based on our previous derivation. We have a Atwood machine, or simply a pulley with two masses, and here is a problem based on it. Consider a cylindrically shaped steel pulley of mass 50 kg suspended from a rigid support with two masses 10 kg and 5 kg attached at either ends of a string taken through the pulley. Okay, if the masses are released from rest, what will be the velocity of the mass system at t is equal to 10 seconds? Okay, very simple question. Question simply demands you to tell if it is released from rest. Obviously, the motion will be like this, anti-clockwise. What will be the velocity? Okay, equation already we have given. Velocity after a time 10 seconds. Okay, the same equation you can use. All data are given in the problem. Please do it and submit the result workout problem in the Google Classroom. And here is another question for you. Again, very simple question. The question is again about Atwood machine. Here is the question. A 200 gram mass M1, you can designate M1, and a 50 gram mass M2 are connected by a string, and the string is stretched over a pulley. Determine the acceleration of the masses and the tension in the string. Okay, so you are releasing it. So what happens? Definitely it will start moving. Okay, one of the mass is greater than the other one. So obviously there will be motion. Pulley will rotate. So you have to find out what will be the acceleration. You can assume pulleys of negligible mass. Okay, so m is 0 here. So find out acceleration. Then what is the tension in the string? Okay, that can be also easily found. T1 minus T2 will be the tension. Okay, so problems are very simple and very interesting. You can do with a lot of enthusiasm. Hope the ideas are clear. Okay, so see you again in the next video. Once again, you are reminded to make note of the entire videos, and definitely we will go through your works whenever the college reopens. So be meticulous in preparing your class notes. All of you watch videos. Okay, then prepare good notes, and as far as possible you can click the subscription link in the YouTube channel and subscribe all the videos. Okay, so with these comments, let us conclude today's video. Thank you all of you.